Hi everybody. Thank you so much for coming. I really love DotNext. Definitely you guys make it happen, so thank you again. No pressure at all. So my name is Dina. Today I'm going to talk to you about this kind of mantra that I'm trying to push forward, and that's automatic monitoring and profiling of your production applications. I like to start my talks with giving some motivation, so that's what we're going to do first. I'm going to try to convince you why it's important and sometimes even a must to monitor your applications on production. Then I'm going to talk a little bit about how we're going to achieve this, our grand plan of self-awareness. And then we're going to have a look at a few examples of some things that you can monitor, some problems that you can monitor, detect, and perhaps even diagnose right there on your production applications. Now, before we continue though, I would like to mention what we're not going to talk about today. So we're not going to talk about profiling tools, external profiling tools. We're not going to talk about any third-party monitoring agents. We're not going to see any dashboards and see how to integrate them with our profiling. Today we're going to do everything with our own bare hands. As I said, we're going to start with some motivation. Why should we monitor our applications? Well, first of all, I'm sure you already have a few ideas of why monitoring is important, but I would like to add my 2 cents about specific things that, from my experience, not everybody usually think about. So, well, first, obviously, whenever we develop anything at scale, if we're writing a server, it's obvious that we need to monitor it. We need to be on top of things. We can't cause any negative value to our clients. Usually, we have too many instances for us to be able to monitor them by hand, and so we obviously have to automate the task. That case is obvious, though. That's what I meant when I said you already know the stuff. What I want to add here is that monitoring is just as important in simple desktop applications, which is, again, something I'm not sure everybody take into consideration when they're planning their applications. And in a sense, the situation with these simple desktop applications is much worse than with servers. Because while you have complete control, usually, over your servers, you know the environment, you know the OS version, the patches, you know what other software is installed, you don't know that about your desktop applications. Once they're shipped to your clients and they install it on their machines, you really don't have any idea what's going on. You don't know, again, you don't have what security software is installed. From my experience, security software tend to mess up with your stuff quite a lot of times. You don't know the patches, you don't know hotfixes, you don't know exact versions. You pretty much don't know what's going on there. And it's not until your clients call you and tell you, hey, something awful has happened, I'm not going to renew our license for next year, that you suddenly realize that we have a problem and you don't have any visibility into what's going on. For all you know, there's even no internet and no connection from you to this production environment at your client's machines. So as I said, in a sense, it's much worse than with servers. There are lots of profiling tools out there, lots of monitoring frameworks. Why should we develop our own? Because that's what we're going to talk about today. Well, I didn't write this on the slide, but personally, I think that investigating performance is really interesting. So at least for me, that's a good enough reason to invest time in these things. But on a more practical note, once you develop your own monitoring and profiling framework, it allows you to customize it to your specific business needs. It means that you can monitor not just the generic stuff as like CPU or memory or disk, I don't know what other generic things are out there, but you can monitor your specific components that actually have impact on your business. So you can monitor startup times, you can monitor queue sizes, you can monitor specific requests, you can monitor execution time of specific components, business critical components in your system. And this is something that's usually not so easy to achieve with the off-the-shelf software, profiling software. Another reason I mentioned here for developing your own framework is that diagnostics data flows from ground up. And what I mean by that is that you don't collect data, redirect it to some external dashboard, wait for it to analyze whatever it is going on, send you an alert, wake up in the middle of the night, start scratching your head, what should I do now? No. The application can actually monitor itself, and once the data is inside the application is aware of this data, it becomes, as the title suggests, self-aware, and it can even act upon these findings. And we will see some examples later of what you can do once you find that there is some sort of problem with your applications. And lastly, that's what all the cool kids do, right? So with the DevOps state of mind, it seems that the community is kind of converging on automating, monitoring, or you know what, basically even automating anything. So of course, in itself, it's not a good reason to do something just because everybody else does it, but they're doing it for the good reasons that we just discussed. So if you need any more convincing, I hope that closes the issue. Okay, so I think we're all convinced now that we should monitor and that we should create our own monitoring scheme. How do we go about it? Because obviously we can't allow ourselves to have a profiler or a debugger continuously attached to our production framework. It's just going to do too much overhead to our systems, and it's not scalable. It's not something we can do. So what I suggest here, and I think it's not very new or innovative, it kind of makes sense, and I suggest that we use some sort of hierarchical monitoring scheme, okay? So we'll use our cheapest tools available, the most lightweight tools that we have, to continuously monitor, well, basically anything. All of our basics. So that's CPU, memory, disk, those queue sizes that I mentioned before, specific requests, basically anything that represents some sort of resource consumption. This can easily be achieved using performance counters, which is a Windows API which allows us to tap into these kind of numerical data providers, which are spread out through the entire system, and they can give us information about CPU usage, disk usage, memory usage, all sorts of .NET related things, such as garbage collection times, generations, and so on and so forth. All of these can be obtained both on the system level and for a specific process, well, namely our specific process. If you don't like using performance counters for some reasons, it's legit. You can just resort to using Win32 APIs. It's just the same because after all the information comes from there anyway. So, whatever works for you. If we encounter some less frequent events, or a situation where we want to gather slightly more data, we can invest more time and resources in our application to collect this data. And this is where things get interesting, because there are tools that will allow us to gather diagnostics data, which will allow us to analyze the situation right there in production and send some interesting data back to development, where the developers, well, that's you, can analyze it further and see whether they can solve this issue. So I'm talking here about rare exceptions or maybe deadlocks that I want to detect, maybe slowdowns in our application. So some of the tools which are available for us for this purpose are ETW, Event Tracing for Windows. Event tracing for Windows is similar to performance counters in the sense that that's an API which allows us to tap into data providers spread out through the entire system. But unlike performance counters, ETW is not limited to just numerical data. Each of its events actually has a whole bunch of metadata attached to it, and that would allow us to collect quite a lot of useful information about what's going on in our system. So that includes call stacks, which is pretty cool for almost all of its events. For example, for GC events, it can contain the type of the GC, why the GC was invoked, which type was being allocated. We're going to see examples of that further on during our demos. So this is a very useful tool. And the overhead of using it mostly depends on the frequency of the events that we want to monitor and the amount of data that we collect using this tool. A complementary tool, which we can use also to get even further information about what's going on in our application, is CLRMD. CLRMD is an open source library that's been available for a few years now, I guess. It's available on NuGet. You can see the code on GitHub. It's maintained by Microsoft. It's a Microsoft API. And what it provides us is that it gives us a programmatic API, a .NET API, for all sorts of debugger-like operations, such as looking at call stacks, traversing the .NET memory, looking at logs, synchronization mechanisms, what else? All sorts of stuff, okay? It also allows us to do the same, well, not all the same, but some of these operations are also available for native applications, which might be important for some of you if you have different layers in your applications, both managed and native. So you should know that it's available, and we're going to see later how it can be very useful for us to do stuff. As for overhead, well, again, it depends. It depends how much how frequently you do that, and what you do once you attach to your application. So for example, getting call stacks of a few threads, that's going to be fast. But traversing a 64 gig memory space, well, not so much. So you have to use it wisely, well, basically like anything when programming. Lastly, if worse comes to worse, then like the end is near and everything is bad and falling apart, you can really take out the big guns and do some massive production profiling or debugging. There are APIs available, the CLR profiling API and the CLR debugging API, and they pretty much give you anything that a debugger or a profiler can do, including pausing the application, going through breakpoints, and so on. Obviously, this is not something we do on a regular basis. In fact, even the documentation itself for these libraries states very clearly that this is not to be used in time-critical code. But know that it exists. If you have a very good reason to use it and to do something with it, then you can. And there are links here to these APIs, so you can have a look at it later. We're not going to talk about them today, both because, well, to tell you the truth, I haven't used them myself. So, I can't tell you too much about it. But I really think it's not something that you're going to use, like, almost never. So I do want you to know that it exists, but probably not going to use it. Lastly, if there are some very specific APIs, low-level APIs that you're interested in, you can hook them, which is an option. And again, I put it here under the invasive and relatively high overhead section, both because it's complicated to do it right. From my experience, there are a lot of security tools that do hooking as well. And when there are multiple tools that try to hook the same API, and one of them doesn't do it correctly, basically all hell is gonna break loose and like it's all gonna come tumbling down, which is bad. So it's not something that you should aim to do. You should try to get your information from other sources, but again, it's a possibility. And the overhead, of course, again, depends on what you do inside this hook. If you do lots of processing, it's gonna take a long time. If you do something fast, then you're okay. So it's up to you to decide. Cool. So I think we're done with all the hand waving, and we can actually now get to business and see some real, well, pseudo-real examples of what you can achieve and what you can learn about your applications. Let's start. The first scenario that I want to tackle is CPU profiling. And although this is a relatively straightforward case, and perhaps not very customized for your own applications, and maybe not exciting, that alone, I think, can give you a really large benefit to your applications, in the sense that a lot of times, Andrei was talking in the keynote about performance testing. He was talking about performance testing during development. But I guess you all, it happened to you all, that everything was fine during development, and then you put your stuff in production, and well, hey, you know, it doesn't work the same as we thought it would, because the client is doing something different, or maybe he has a different Windows version. And again, I'm talking here about the case of a desktop application, where the environment can be very different between many clients. And things don't work as you planned, and you don't know how to reproduce it, and it's kind of flaky anyway, it doesn't happen all the time. Once in 3 days, CPU goes high for like 10 seconds. And your clients are really upset because they're really important people, and those 10 seconds ruin their lives, okay? So, and you don't know what to do. Now imagine you could, in real time, collect information, profiling information about what was going on in your application, simply write it down to the log, and ship it to developers, to the development. That would be awesome, and that's what we're going to see in a moment. So, how are we going to achieve this amazing goal of ours? Well, like I said before, we're going to implement a hierarchical monitoring scheme. So, first, we need to detect the problem. Detecting the problem is easy. We use performance counters or whatever to continuously monitor our CPU usage. This is really cheap. It's not something, unless you're developing like a really real-time system, it's not something that we shouldn't be able to do quite frequently. And then we can define rules that we want to live by. For example, my application cannot use more than 80% CPU for over 10 seconds straight, for example. Okay, obviously, you need to define what it is that works good for you or your clients, or whoever in your organization that defines performance. So we can do that, and once we detect this situation, we detect that we're currently live inside a problem. Then we can invest more resources in order to try to detect the source of this problem, to diagnose it, to get call stacks. And this is something that we're going to do with ETW, which, as you recall, I said was able to provide call stacks of the events that it's monitoring. And specifically for CPU, it turns out that ETW is able to simply sample the CPU every, say, 100 milliseconds. That's the default. And by simply pinging the CPU every 100 milliseconds, we actually get the same result as a sampling profiler would attached to our application. And so we can do that in real time and using an open source library called LiveStacks, which allows us to translate these samples, these ETW samples, to actual function names. This would allow us to rebuild call stack trees, find the most CPU-consuming call stacks, produce flame graphs, or whatever it is that we want to, whatever is more convenient for us to display the data. And in fact, we can even suggest recommendations as to what to do, like right now, in real time, about what's going on. If you're wondering what on earth we could suggest to do in real time, here are a few examples, but I'm sure you can think of more which are related to your line of business. So one example would be if your authentication controller suddenly takes too much CPU. Well, perhaps you're being attacked. So, well, I don't know if there's anything specific you can do about it, but like maybe you could close down communication, maybe you could filter some IPs. I don't know, I'm not a web expert, but I think there are things that you can do about it. Or for example, if you have some processing component that is suddenly overworked, suddenly uses too much CPU, well, maybe it's time to scale if you're a server. And in fact, if you could automatically scale, that would be double the fun. So that's awesome. And well, you know, eventually, at the very least, if you don't have anything smart to say or do at that specific point, at least you can write down all the information in your log files and ship it back to development. So I'm sure that the developers are going to be very grateful for getting all of this information when the client complains that your CPU was overworked. So let's see an example. I have a ASP.NET web server called Los Gatos. I pre-recorded all the demos because like things get to be flaky and I don't want to, you know, I want everything to work perfectly. So we're going to see an example of an operation that I'm trying to do in this website and what happens when I try to do that. So what I have here is I have here on the left side our website, and on the, oh, sorry, you saw the end result before you were supposed to. So I have the website on the left side, and I have perfmon, which is a UI for listening to performance counters, and specifically I set it to monitor processor time. So I'm going to try to do something with my website, and I'm going to monitor CPU. I'm going to log in to our amazing cat website. And once I try to log in, it looks like the CPU is going crazy for a while, and then it goes back down. All right? Now, this is something that doesn't happen all the time. In our case, it doesn't last very long. So it's not like the client or whoever can call you and tell you, please come quick, attach a profiler to my server and, you know, check whatever it is going on. Because by the time that you pick up the phone, the scenario is going to end. So it would be very nice if we could get data in real time. Let's see what we can learn about this situation. So I'll open my Visual Studio here, and we'll look at some code. This is the CPU monitor. Now, one thing I want to say before we start, you're going to see lots of classes and inheritance and stuff. I am not sure that this is the best way, like architecture-wise, design-wise, to achieve this goal. So don't like go copying the code exactly as it is to your systems. Think a little about it. This is just a demo. And so the code is accordingly planned, but it should give you an idea of what you can do, how you can do it. We're also not going to go into too much specifics because I'm sure you can read API documentation on your own and, you know, get a lot of ideas about what can be done. I mostly want to motivate you and give you inspiration for what you can do. So this is our CPU monitor. It inherits from event stack monitor, which in turn, excuse me, go to definition, sorry, which in turn inherits from monitor, and this is what we're going to start with. So this class monitor represents this basic idea of continuously sampling some performance counter, in our case, every 1 second, and it's going to monitor for violations of our rules. And once we hit 3 consecutive violations, it's going to invoke something that I call intensive mode. So let's look at that. This is basically what we do here. In a loop, in a timer, every 1 second, we get the next value of our performance counter if it passed our threshold and the number of violations is high enough we invoke the sample intensively mode. And sample intensively mode is implemented in the child classes, which is what makes it a CPU monitor or a memory monitor or a GC monitor, which are things that we're going to see next. So let's look specifically at the CPU monitor. Remember that it's an event stacks monitor, and we're going to get to it in a moment. But you can see what the threshold is. So we're monitoring for 19% CPU. And you can see the performance counter that we're using. That's percentage of processor time, specifically the total percentage of processor time for our process. Now, in the case of CPU monitoring, what we want is to get the call stacks, right? We want to profile our applications. And this is what is achieved in the event stacks monitor. I'll go back to it. And we can see the implementation of the intensive sampling function. What we see here, and this is the part that I'm going to kind of skip over a little, just believe me that it works. Generally, what we do here is that we get our process, we create a live session, and I'll get back to it in a moment. This live session, it kind of wraps the ETW, which allows us to get the call stacks later. I'll get back to it in a moment. We start the session. We wait for some time. I think it's 5 seconds, if I remember correctly in this scenario. We stop the session. And after the session is done collecting the data, all we have to do is access the stacks property that it has, which specifically has a top stacks method, which provides us with the stacks that use the most CPU during the recording of this session. And then what we do is simply write down all of these stacks to our log file. If you're wondering what this resolve is, this resolve method translates memory function addresses to function names so that we as developers can understand what these addresses mean, so we can actually go later to the code and find what it is that was causing the problem. And now I will go back to this live session class. We're not going to go inside it. It is copied from the GitHub repo live stacks. And it simply is a little wrapper around ETW, which customizes the events that need to be collected in order to get sampling information from the CPU for our application. So, but this is the concept. Start an ETW session, collect for a while, translate call stacks, function addresses to concrete method names, and output it to our log file. So that's pretty straightforward. Let's see the log file that was produced during our attempt to log into the application. So this is a log file that I have. CPU log file. And you can see that at first everything was fine and the CPU was low. But then after a while, enough violations were detected 3 times. And so we started the sampling mode, the CPU sampling mode. And after 5 seconds or 10 seconds, I don't remember exactly, we got enough data. And we wrote to the log file the top 3 call stacks, which were consuming most CPU time. So let's look at them. Well, first there are some addresses that were not translated, which is a shame. It could be because we don't have symbols to these components, which is possible, because Microsoft don't always have symbols for everything, which is a shame, but that's the way it is. But anyway, we go down here, and what we can see, and this is a little maybe disappointing, and I'm going to talk about it later after all the demos, it would seem that the first call stack actually tells us that the monitoring itself is using some resources. And remember that? I'm going to come back to it later. But this is one reason for using high CPU. But you see, this is interesting because this only happened because of the high CPU usage that happened on login. So it doesn't mean that we constantly use too much CPU due to this monitoring, as it was only invoked when high CPU was detected. So just keep it in mind. Then the next call stack that we have is here. And what you can see here, and I'm not an ASP.NET expert. Basically, these simple websites is all I know how to do. But you can see that there's a lot of stuff here going on which has to do with like ASP.NET itself. Now, again, truly, I don't know if there's anything we can do about it. But I think it's interesting information, or at the very least, it doesn't hurt us to know that there's something there going on. And I'm sure that the ASP.NET MVC experts perhaps do have the knowledge to assess whether this is something that can be fixed. Maybe we're not writing code like with the best practices or whatever. Finally, we'll get to the third call stack. It's down here. And good. And here we can finally see some interesting results from our application, specifically from the login method, which is not a surprise because it happened during login. Do remember, though, that when we get this information later on, we don't necessarily know what was happening during the CPU spike. Like, we saw the video of trying to log in and the CPU going up. But like when customers later complain, we don't necessarily know what was happening. So in any case, yes, there was a problem in the login function. And specifically, if we see here, we see that there is some hash function that was being calculated. And we can go to the code now, to the account controller, I believe. Let's search for this good hash function. Yes, very well. This is our login method. And we can see that whenever an email ends with Gmail, we do some hash calculations, which apparently take lots of CPU. So we detected in real time that there's a problem with CPU usage. We started profiling, and we got the exact function, the exact location in our code that was consuming all the CPU, which is pretty cool. Now, you probably can't see very well, so I'm going to describe to you exactly what's going on here. This is a screenshot of Visual Studio. This is Visual Studio here. And this is Process Explorer. This is the devenv process. And, well, you can check on your own computers. But it seems that the devenv process has a child process called perf watson2. And this perf watson2, perf for performance, hint, hint, this perf watson2, as you can see in the performance monitor window, actually creates an ETW session with 4 ETW providers, which I actually wasn't able to determine what exactly they record. However, this process is in charge of profiling Visual Studio. So the people who developed Visual Studio felt that they wanted to have more telemetry about what was going on inside Visual Studio, and they actually employed the same method that I showed you just now with CPU. So to tell you the truth, I'm not sure what it is exactly that they monitor, because I wasn't able to put my hands on a file that they recorded. I got some weird errors, never mind. But this is a documented feature. They monitor themselves using ETW. So it's not something that I invented even. It's something that people actually do. So just remember this as we go through our next demos, that this is not just examples, this is from real life. So next demo, we're going to talk about GC monitoring. Or rather, monitoring problems that can affect GC performance. Specifically, what we're going to talk about is monitoring high allocation rates. Because once we do too many allocations, obviously this can affect GC. And again, I want to add here, it is obvious that GC pauses when serving requests are bad. But I don't want you to forget your simple desktop applications. Because if your users experience glitches in UI, the UI getting stuck because of GC pauses, because of long GC pauses, they're going to get upset. So again, I just want to stress out that all these things that we're talking about are relevant for all sorts of applications, not just servers, also the simple things. So what are we going to do? Again, very similar to the CPU scenario, but with memory. We're going to monitor using performance counters the rate of allocations. Once we see that there are too many allocations happening, we can start the intensive profiling. What are we going to do in this case in the intensive profiling? We're actually going to get data about allocations, which types are being allocated, where they're being allocated. We can also collect data about how long GC is taking, about the generations, about how much memory is freed, how much stays. We can even attach CLRMD, and we're going to see that, and get an overview of what's going on in our heap. Segments, again, generations, types of objects, numbers of objects. All of this can help us get an overview of what's going on in our application and try to understand where the problem occurred, what's the root cause of our problem. So let's see an example. Again, we'll start with a video. We have our application, and this time I'm monitoring the rate of allocations. So I'm going to go to the About page, and suddenly you can see lots and lots and lots of allocations. Now, it doesn't necessarily mean that we're going to get a GC problem, but it's an interesting thing to know, because it might cause a GC problem. So that's something that we might want to get more information about. What did I do? Stop. Let's look at some code. Let's look at some code. We are going to go to our allocation monitor. This is also a kind of event stack monitor, which, as you remember, is a kind of monitor. And the reason that it's an event stack monitor is that we're going to be interested in the call stacks of where allocations are happening. Remember, just like CPU, we detected too much usage of CPU. We wanted to call stacks of CPU. This time, we detected too much allocations, so we want to get call stacks of where allocations are happening. And ETW is going to give us just that. So first, we can see, again, that we're monitoring the allocated bytes performance counter. This is the threshold that we decided. And again, of course, you're going to decide on whatever it is that works for your application, for your business needs. And the ETW event that we are going to listen to and collect call stacks from is the CLR-GC-GC allocation tick. This event is going to give us data about the type that's being allocated and where it's being allocated. So we catch this event, this ETW event, in the onEventOccurred function. And this GC allocation tick trace data structure, it has a property telling us how much data, how much memory was allocated. It has information about the type that was allocated. It has lots of other data as well, but this is what we're going to use. And in our specific case, during the intensive sampling mode, what we're going to do is that we're just going to keep this data in a dictionary. And so we're going to have information about how much of each type was allocated during the intensive sampling mode, which can be useful. And again, along with that, we're going to get the call stacks that made those allocations. And along with this information, after we collect these statistics for a while, we're also going to attach to the heap and just get like statistics about what's currently going on in the heap. And this is something that we're going to achieve using the CLRMD library. And it's fairly simple. There are lots of lines of code here, but like they're really simple. The main API you should be familiar with is attached to process. In our case, it's our specific process. We get the CLR runtime. That's just a technicality. That's like not the point. And then once we have the runtime in our hands, it has a property called heap, which gives us access to traversing the heap. It has the total heap size. It has generation sizes. But what's even more interesting is that it allows us to enumerate the entire heap. And for each of the object, get the type, get the size, and again, put all of this data. This is like a long link query, but it's, again, that's not what's interesting here. The interesting part is this function, enumerating objects, and the type, size, and name properties that are given for us for each of these objects. And then we can just put all of this data into a dictionary to letting us know, currently in the heap, we have so-and-so strings, we have so-and-so arrays, we have so-and-so, I don't know, whatever, something else, okay? So let's look at the results. This is our log from the allocations. So at first, everything was fine. And then allocations started happening, and then we got enough violations. And remember that we collected call stacks from where allocations were happening. So these are the top call stacks. Sorry, these are the top allocation-consuming call stacks. And you can see straight away, this time we get the result immediately. It comes from the about method, which is not surprising, because again, we know that that's what we did on the website when the allocation started happening. But specifically, it's all coming from concatenating strings, which is weird. So let's look at the code. About controller, where is it? It's in the home, probably. Sorry, home, controller, about, yes, okay. And we see that the about method does quite a lot of XML parsing. And specifically, it calls some append functions and so on. And so we're dealing with a lot of strings here and a lot of intermediate objects and concatenating stuff, writing. And so we get an allocation problem. Problem found. Let's see what else we have here, because remember, I also printed the heap breakdown. So in our specific case, we found the problem already just by looking at the stack, but it's interesting to see what other information was available for us. So after all of these call stacks, yes, so after all of these call stacks, we also get this general statistical information about the heap, which is, very interesting, could be very interesting, and indeed in our case, that we see that most of the allocations were, oh, I'm sorry, this is still from the ETW. This is the statistical data that we have. This is the total heap size. These are the generations. And these are all the objects that we have in memory. And indeed, we can see that there's like a huge amount of strings. So we're pretty sure that we found the root cause of our problem. Next. Next, we're going to continue investigating memory problems, but this time we're going to talk about the much feared scenario of a memory leak. Now, a memory leak is something that there's no point in collecting call stacks for, right? We just know that currently there's a problem, we have too much memory. So we are going to follow the same scheme of monitoring memory usage. We could monitor it for a while and detect that memory is going up and say, well, perhaps we have a memory leak. Or, it's not for sure that we have a memory leak, but it's possible. So we might want to diagnose that. But also maybe we just want to say that, listen, there's a rule that our application cannot use more than, 100 mega of memory. Right? So once we pass that threshold, even if we don't think it's a memory leak, it's just way too much memory. Once we do that, we can use CLRMD very similarly to what we just saw and analyze what it is that's taking so much memory in our memory space. If we are afraid that we have a leak, we might try to automate what we would do as developers during development. We might take several snapshots of the heap and try to compare them and see what was allocated, what was freed, what wasn't freed, why wasn't it freed. All of this is available using CLRMD. And if we're willing to invest even further and try to correlate this data with some information that we collect from ETW about allocations, it can help us even further. So let's see the demo. Memory leak. Again, we're going to do something with the website and see how memory behaves. This time, I'm monitoring bytes in all heaps. That's our managed memory. So I'm trying to register to the website, and memory seems pretty constant so far, which is good. At least just typing doesn't do anything bad. And then we try to register. Still OK, and OK. Memory just rose. Now, it's not necessarily a problem. Now, I'm not going to wait any longer because I don't want to waste any time, but trust me, it continues going, up and up and up and up. But again, even if we don't suspect a leak, maybe we just want to know what it is that's, taking all this memory in my process. So let's see what we can do. We have our leak monitor. So this leak monitor, this time it's only a type of monitor because there's no meaning to collecting call stacks. There's no ETW event that we can use to diagnose the current situation of using too much memory. So we have our threshold and we're monitoring bytes in all heaps. Let's see what we do when we actually detect that we have a high memory usage. So I'm going to try, like I said before, to automate what I would do as a developer in development. We will take several snapshots. In our case, that's three snapshots of the memory space. Now note here that I'm collecting, that I'm calling GC collect before. That's because I want clean statistical data about what's going on, because I'm going to later, after I collect these snapshots, I'm going to compare what was freed and what was not freed. So I need kind of a clean working set of data. So I collect garbage, I attach to the process, I get a heap snapshot, we'll see it in a moment, I wait a few seconds, I do it again and again for 3 times, if I remember correctly. And after I'm done taking all these snapshots, I go over them, compare them. We're going to see the code in a moment. It's very simple. And write the results to a file. So let's just look at the heap snapshot. This is a kind of primitive heap snapshot. I'm not going to collect statistics about specific objects. Obviously, it's going to be more time-consuming, and it depends on whether you want to invest that time in your process or not, but it's possible. Here we're doing something relatively simple, just collecting statistics of number of objects by type and the size, total size of allocations by type. And this is done in the exact same way that we already saw in the previous demo. Traverse the heap, get the type, get the size, get the name, put it all into 2 dictionaries, size by type and count by type. So this is the heap snapshot, and it's very easy. To compare the heap snapshots, well, again, this is not even using, obviously, CLRMDs. This is just some logical function that goes over our 2 dictionaries and checks how many strings did I have before, how many strings do I have now, how many arrays did I have before, how many arrays did I have now. And then we simply just output all of this data into our log file. So let's see the log file. At first, everything was fine, as you remember. And then time went by, and memory started increasing. And our monitor detected that there is a breach of rules in our application. We collected 3 snapshots. And what we can see here is the differences, the comparisons between the snapshots. So I'll go straight down here. And what you can see here is that the amount of byte arrays increased very significantly between these snapshots, between these 2 snapshots. But we can also see the same behavior with the second snapshot. So obviously we have a problem with byte arrays. Now, specifically byte arrays are a bit problematic because they might occur like basically anywhere. So hopefully what you would discover is some application-specific type that you have, which would allow you to go to the code and search for whatever it is that was happening. But seeing that I wrote the code, and I know that it was happening during registration, I can now go to the account controller, to the register function, which I see that, is it this one? Sorry. No. You know what? I'll go straight down here, because I know that's where the result is. So our register function, oh yes, we saw that before. Our register function checks the password that you tried to enter to see that it's valid or whatever. And when checking this password, it adds some data into this static list. And the data that it adds, incidentally, allocates quite a large byte array. So I know this is not a very realistic example, but I do believe that in real life you would have a specific data structure that you would be able to detect. But plus, even if it's a byte array, I mean, you should know where in your code you allocate byte arrays. Or again, and we didn't implement this here, but you could correlate this with the allocation ETW data that we have, and maybe see that you have quite a lot of allocations in this specific code path. So the last demo that we're going to do today for dessert is deadlock detection. Now, deadlock detection is a little different than the other examples that we saw, in the sense that it's not straightforward to detect that we have a deadlock. We don't have a simple numerical metric that tells us, hey, you have a deadlock. It's not like, hey, you're using too much memory, hey, you're using too much CPU, hey, you have too many allocations. It's not clear when we have a deadlock. So I have a few examples here of what might suggest that you have a deadlock, but you should think about your specific application and try to describe, to define how you can detect that you have a deadlock. But a few examples are low CPU. If your application is suddenly doing nothing, you might be deadlocked. Another example is requests suddenly start timing out. Maybe the threads which are supposed to answer these requests are stuck. Or on the other end, maybe suddenly your thread pool keeps opening more and more and more and more threads because, like, you know, the other threads are deadlocked and it has to serve requests. So these are a few examples, but again, think about your own business needs. And so what we're going to do once we suspect there is a deadlock is that we're going to attach CLRMD. We're going to look at the call stacks, and we're going to try to analyze whether we have a deadlock. Now, specifically for the case of a deadlock, I'm not sure that there is something you can do to solve it. I don't know, pray for a miracle. But again, at the very least, you report the problem in your log files and ship it to development. So let's see. I'm going to try to go to the contact page. And we're not going to wait a long time. Believe me, it's stuck. This is the CPU. It's doing nothing, and the page just doesn't load. So we think there might be a deadlock. Let's look at the code. Deadlock monitor. So in this example, I didn't implement detecting the deadlock because there are many examples, many solutions possible, and we saw enough examples of that already, I think. So what I'm just going to show you is how easy it is to access call stack data using CLRMD and basically check whether there is a cycle in the thread weight graph. So what we're going to do is every few seconds or whatever, start a method, find deadlocks, which is really pretty basic recursion. We're not going to cover the algorithmic part of this method. But mainly what it does is that it goes over all of the threads, which we have access to from CLRMD. And for each of these threads, it's going to traverse all of the objects that this thread is waiting for, which we can very easily access. Excuse me, where is it? Which we can very easily access using the blocking objects property of a thread. And each of these blocking objects have an owner, which is, well, another thread. And so these properties together, having access to the threads, to their blocking objects, and to their owning, and to their owners of these blocking objects, all these together allow us to just construct a graph of what's going on in our application and find whether there is a cycle. And once we find a cycle, we can simply get the call stack of where this cycle is happening and output it to our log file. And indeed, if we look at the log file, we can see that a deadlock was detected. It was detected specifically in the home controller in a process detailed function. You have the thread IDs and everything. And indeed, if I go to the home controller and I go to the process details function, I can see that it has two locks, first and second, and it actually calls itself, only exchanging the order of the locks, and this is textbook deadlock. So we have a deadlock, and in the log file, we have the exact place where this deadlock occurred, which I think is pretty cool. So that was our last demo for today. And the time that we have left, I want to tell you some more general things. Obviously, there are many more scenarios possible. There's not enough time to discuss everything, and you need to think about what's good for your business. So, but a few examples. For example, you could monitor heap fragmentation, because the CLR is not going to compact the large object heap for you unless you specifically ask for it, because it takes a long time. So if you monitor heap fragmentation, you can actually make an educated decision on whether you want to invest the time in compacting the large object heap or not. So interesting idea. And another option is something I didn't talk about a lot, is native. All of our examples were of managed code, but you can use ETW to try to diagnose a native memory leak as well, because you can actually get events of where allocations are happening in native code as well. So that would be an interesting experiment. As a side note, I also want to mention, and again, we didn't talk about this, but CLRMD, it can connect to, it doesn't only work on running processes. You can actually use it to connect to a crash dump and automate crash dump analysis. So just know that it's possible that if you have crashes in your applications, you can also automate the process of analyzing it, or at the very least doing some triage, like looking at the call stacks, finding the faulting component. And if you do that, it would be even best if you can aggregate all of the crashes that are of the same type, and maybe even automate opening bug reports for your developments. So that would be a good idea. And lastly, and this is very important, it's obvious what the benefits are, because you have visibility into your application, but you don't have to grow the team as your application scales. But there are downsides which you shouldn't forget. The first one is obviously complexity. You add more code, you add more complexity to your system, and that means that more things can fail. However, you can try to reduce the risk by doing all of the things that we saw in a different process. Although in our examples, the monitoring occurred inside the process itself, there's mainly almost nothing preventing you from doing the same thing from an outside watchdog process. ETW and performance counters are collected system-wide anyway. CLRMD can connect to another process. It doesn't have to be to my own process. So you can totally reduce the risk like that. Second, there's overhead, and you already saw the example in our first demo, where the first call stack was from the ETW collection itself. So you should totally be aware of that. And in fact, if you search perf Watson 2 online, you're going to see a whole bunch of questions, people asking, how can I shut it down? It's, using my resources. So you should remember that. And lastly, more development, more features means more development time. But that's for you or your managers or whoever to decide whether the benefits are worth the time. So that's it for today. We saw why it's important to monitor, or rather diagnose, on production, no matter what kind of deployment or processes or application you're developing for. We saw how to tackle the issue by a hierarchical monitoring scheme, use lightweight monitoring for detection, invest more resources to diagnose. And we saw 4 scenarios where we found real problems in our code: CPU, memory, deadlocks, which I thought was pretty cool. All the demos are online. I'm pretty sure you're going to get the slides from DotNext people, so don't worry about it. Thank you.